All right, thanks, Alan, and thanks everybody for joining us today. We certainly appreciate your time and you dialing in. To get things started, I just want to talk briefly about what I'm going to cover in the webinar. I do want to start just telling you a little bit about us, since some of you probably have not heard of us or haven't worked with us in the past. Then I'll get into what is software-defined hardware. What are we talking about when we say that? And I'll talk a little bit about the technology advances that made software-defined hardware possible, and in fact made it more popular in recent years. The use of this technology is actually ramping up. Then I'll talk a little bit about what software-defined hardware means for you. And I'll introduce a couple of our systems that utilize the technology, which will set us up nicely for a few examples of where we've used software-defined hardware to benefit our customers. So really quickly, a little bit about us. We are a global leader in optical and data networking equipment. We have customers in over 70+ countries with over 500,000 network elements deployed. We have more than 10,000 here in North America. So in the past, we have traditionally sold through partners that actually use their branding on our products. In fact, some of those partners were some of the bigger providers here in North America. So you actually may have seen our equipment or used our equipment and not even known it. You used it under a different brand. So we have a broad range of services and technologies. I'll talk about two of our major products today when I talk about how we utilize software-defined hardware. But basically, we specialize in ultra-converged platforms. The two that I'm going to show today are an ultra-converged OTN switching and WDM transport, and an ultra-converged broadband platform. I will not talk about our management system today, but I did want to mention it. We use a single management system for all of our products. Our products provide layer 0 through layer 3 capabilities, which means the manager has to be multi-layered and fully functioned. And because we manage all those layers ourselves, we can provide benefits to you, like being able to correlate alarms across layers or show how layer 2 services traverse the optical network, that type of thing. Software-defined hardware is one of our own brands, but it's a technique used by a lot of hardware providers. I'll show you what it is in a few minutes. And then finally, we architect our products to be future ready. And part of that is the software-defined hardware, and I'll talk about how that plays in when I get to that. And part of that is the way we build our chassis and our cards and things like that. We structure them so that we can provide multiple generations in the same chassis to prolong the life of those products for you. So as an example, the switching product I'll talk about today has gone through multiple generations of switching fabrics without swapping out client cards and without swapping out the chassis themselves. We simply upgrade the fabrics, and the WDM platform I'm talking about today has gone through multiple generations of WDM rates, ranging from 10 gig today, 10 gig to 200 gig today, and 400 gig and 600 gig this fall. All right, so with that, what is software-defined hardware? What we're basically talking about is utilizing FPGA technology to solve problems. So for those of you who I'm sure you've heard the term, but for those of you who aren't familiar with what an FPGA is, it's a field programmable gate array. So it's a piece of hardware that we can basically program to do almost anything we want it to do. And the beauty of the technology is that it actually, once you program it, it actually has the equivalent performance of running natively in hardware. All right? We use it to provide field programmability and the flexibility of the hardware, which we'll talk about in a few minutes. And it's generally used to implement features that are time sensitive. So a lot of the technologies that you hear about to provide flexibility and the capability of the hardware are things like NFE. And those technologies are actually executed in the software. In fact, NFE is executed as a virtual machine, which has dependencies on the operating system and on a CPU, an external processor, which makes them very latency intensive. And we'll talk about the types of things that we go after with FPGAs. So what do we use FPGAs for in our system? Number one is to right-size these latency-sensitive applications like switching. So for instance, we build our own OTN switching fabric in FPGA technology, which allows us then to build only the amount of fabric we need. So at the time we built our switch, the fabrics that were available were too large for what we were looking for. So we didn't want to pay for that extra cost and have to pass that on to our customers. Introduction ahead of the market of new technology. So if a standard comes out, it usually takes some time for integrated circuit providers to provide technology for that. So with the FPGA technology, we can develop new technologies ahead of the market, and I'll talk about that as I go through the presentation. Customize add-ons to off-the-shelf technology. So even if we're using off-the-shelf technology, we'll sometimes drop down an FPGA to augment that technology. So for instance, that's actually a common technique with Ethernet switches. There are tons of Ethernet switches out there. You can generally buy one that's right sized. So, but the right size technology may not have all the features that you need. So sometimes you'll drop down an FPGA and just add those extra features. Common thing to do that with is O&M capability like 2544 or Y1731. Implementing functions in hardware without the long associated cycles of ASICs. So ASICs is another programmable technology, but once you program the technology, it's fixed. So you can't program it in the field, you can't change it once you ship it. And each of those ASICs is very, very expensive to build and takes a very, very long time. So FPGAs are a wonderful technology that is an alternative to that. And we also use it to produce ultra-converged technology and reduce the cost through integration. So what I mean by that is sometimes when we want to stick more things in a piece of hardware that the integrated circuit market is prepared for, generally they'll provide the capabilities that we need on multiple integrated circuits. And so what we'll do is we'll combine them all on our own FPGA, which will reduce the cost of the system as a whole. So what's been going on that's making this more prevalent today than it has been in the past? We've used in the Ethernet switching and transport market, we've used FPGAs for a long time, but it's becoming more and more prevalent. And the reason for that is advances in the FPGA technology. I mean, it's absolutely amazing. If you look at this IEEE graph of FPGA technology in the last 30 years, basically what they're saying is that in terms of price and power, they've come down on the order of 1,000 times. And in terms of capacity, they've increased on the order of 7,000 or 8,000 times. And in terms of speed, they've increased like 100 times. And in fact, as we get these advances, they become closer to closer producing the technology on an integrated circuit or buying off-the-shelf technology. So they become very, very close, actually. And to give you an example, in 2011, the biggest FPGA that was out there had 6.8 billion transistors. At the end of last year, Intel introduced one that was 43.3 billion. And by the way, the telecom industry is one of the leading industries in using this FPGA technology. But an important thing to note is it's used across many technologies. So we benefit from the volume. Most hardware technology cost is driven by volume, and we benefit from the volume across multiple industries. So that's what makes it relatively inexpensive for us to use. All right, so what does this do for you in the end? So number one, it allows us to produce products that span multiple generations. So when we put out a new line card or even a fabric or a fabric that provides certain O&M capability, we're not done with it then. So we can do things to extend the functionality of fabrics and line cards in these FPGAs without even having to respin the fabric or line card. So we can even upgrade stuff in the field. Which allows us to prolong the life of those chassis. So we can provide you new protocols, for instance, new O&M capabilities without having to even introduce new fabrics and new line cards. Lower the cost of total ownership. I talked about that on the previous slide. Basically, by combining capabilities of multiple integrated circuits that we would have bought off the shelf, we can lower the cost of these things. We can also right-size the hardware and build things that are custom sized for our particular application. Deliver customized features. So one of the great things is that it's relatively inexpensive to develop on these things. So it's certainly as compared to respinning a card. So if my customer wants something that would have required respinning a card without the FPGAs, but we have these devices on our system, we can, if we had to respin the card. For example, on our Ethernet switching platform, we added SONET switching capability. Initially, the SONET interfaces didn't have OTN wrapping and FEC. We had a number of customers that had long routes that could benefit by eliminating amplifiers if we added FEC. We did it in a matter of months and saved those customers lots of money. Time to market advantage. If there are new technologies, as I mentioned, that aren't integrated in off-the-shelf stuff, we can do it ourselves. Design reuse. So if we buy stuff off the shelf, we can't really reuse the intellectual property on that chip if we need what's on that chip plus a little extra stuff. With FPGAs, we can actually port the technology from one FPGA generation to the next and then just build on top of that. So we reuse the technology that we've already done. In fact, people like ourselves have libraries of things that we can implement, like different FETs and different protocols that we can just drop down on these chips and build custom configurations for customers. Field upgrades on install base, I've already talked about, but of course we can upgrade things in the field, as I've mentioned before. All right, so what are we doing to our platforms? And this will give you a good example of what types of things we can do with FPGAs that benefit our customers. And so the two platforms that I'm going to talk about today, because we use FPGAs extensively, are our OTN switching and optical transport platform, the TJ1600, and our Ethernet switching ultra converged broadband access platform that also provides PON, circuit emulation, and WDM optics all on the same platform, made possible by this technology that we're talking about. So just so you know, both of these platforms come in multiple different sizes with multiple different fabrics. Both of them are fully redundant in terms of fabrics, power supplies, fans, controllers, but I'm not going to talk about the platforms in detail. I'm just going to get into how we use the programmable technology. So the TJ1600, the OTN switching and optical transport platform, uses FPGAs throughout. We use it for almost every major feature that we implement on that platform. And I'll give some examples as to how that's benefited our customers. The fabrics, we have built a number of different fabrics for the platform to scale for the different chassis sizes. And we have up to a terabit fabric, which we've implemented ourselves. We use FPGAs for the transponders. So not only for client framing, but for FEC and moving traffic from the client interfaces to the line interfaces. We use FPGAs for muxes. We don't buy off-the-shelf muxing hardware. We build it all ourselves. On the ultra-converged broadband platform, we do use off-the-shelf technology for the Ethernet fabrics. And the reason for that is that every industry uses Ethernet, so you basically can find Ethernet fabrics in all sorts of sizes and right size for almost any application you want to do. So we go ahead and use things off the shelf, but we augment those technologies with our own FPGAs, and I'll show you an example of that a little later, but I talked about it a little earlier. So we do provide things like O&M capabilities that aren't native on those off-the-shelf technologies so that we can enhance them. We use FPGA technology also, for instance, to provide a SONET interface on this platform because we had some customers that wanted SONET switching for legacy migration. And instead of adding instead of buying an off-the-shelf SONET fabric, which are hard to come by nowadays, and also even if we found one, we couldn't guarantee how long it would last in terms of how long that vendor would keep it on the shelf. Because as you can imagine, those fabrics aren't used all that often anymore. So by building it ourselves, we can control that for our customers. And we built a circuit emulation function on this platform as well using our FPGA technology, which is actually one of my examples. So let's get into the examples. The first one is the 1600, which remember was the converged OTN switching and WDM transport platform. On most platforms like that in the field, you'll see three types of line cards. You'll see a switch line card, which has client and line interfaces. Maybe some only have client, some only have line, and then they switch across the backplane, and you can switch from one card to the other. So you can switch from one card's client to another card's lines. Then they generally have devices that act just as WDM transponders. So basically, you go in one client, 1310 optics, and you go out WDM optics on the back end. And then they have another card generally for mux bonders. And the reason these cards are built this way is because the off-the-shelf chipsets that you can buy are well suited for building them this way. Now, what we did was we combined all those capabilities into a single card. In fact, I'm going to show one card, but we have multiple cards on the system that do this with different interface types and different capabilities. But we were able to do it because we can combine all of those capabilities on an FPGA. And now the other reasons that people put them on separate cards is to save cost, right? They think combining those capabilities, buying all those integrated circuits off the shelf, will then make a switching blade more expensive if I also put mux bonding and transport capability on it. Or a mux bonder blade more expensive if I also put switching capability on it. But we get around that because we've combined all those functions onto a single FPGA that would normally be separate devices. And with the cost curves of FPGAs where they are, it actually doesn't add more cost in the end. All right. These devices are fully pluggable. In fact, most of the cost in these devices is in the optics. So if you're doing a transponder function and you buy our blade, you don't want to use the mux bonder or the switching capability, so you don't need all the ports, you don't pay for them. You basically pay as you grow by using pluggable optics. Your sparing costs are reduced by 2/3 because you get rid of a lot of these blades. The particular blade I'm showing you acts as a transponder and mux bonder, as I mentioned. So the one I'm showing you acts as a 10 gig transponder, so it'll provide multiple 10 gig transponders, or it will provide a 10 by 10 gig into a 100 gig line. So the beauty of that is you can deploy 10 gig transponders today and not incur the cost of the optics till you need them. And then if you want to save wavelengths, for instance, and mux those 10 gigs into a single 100 gig, you can do that with the same card. So you don't have to buy a new card, buy the same card, or use the same card, plug in the optics, you're good to go. In addition, because we use FPGAs everywhere in this particular line card, we can add protocols, new protocols, even while these things are in the field. So today we provide OTN clients, Ethernet clients, SONET and SDH clients, fiber channel clients. So say, for instance, we wanted to add CIPRI clients. We could do that as well on the same card after the fact. All right. Use case number 2, single fiber. So you might be wondering, what in the world could single fiber transmission have to do with FPGAs? Well, so first of all, what I'm talking about when I say single fiber transmission is, as you know, when you buy a WDM system, it transmits and receives on separate fibers. So you always buy a fiber pair. And as you know, fiber is expensive, so sometimes you don't necessarily want to do that. But what enables that is at 10 gig, you could transmit or receive, and most 10 gig transceivers, you transmit it and receive on the same wavelength. So basically, you put all those transmit wavelengths on one fiber, and you put all those receive wavelengths on another fiber. And 10 gig transceivers can do that fairly readily. And then if you want to do single fiber, what you do is you have to transmit and receive on different wavelengths so that you can put both of those wavelengths on the same fiber and they don't bump into each other. And 10 gig transceivers could do that fairly readily because they had wideband receivers and they had tunable transmitters. So all was good. Problem is 100 gig, you don't see a lot of WDM vendors that have single fiber solutions. And the reason is because of the way coherent receivers work for 100 gig. So the way they work is they expect an optical signal coming in, your WDM signal from the other side of the network that's being transmitted is received, and then they have a second laser on the device that acts as a reference. It's called a local oscillator, and it's merged with the incoming signal, and it's used by the DSP as a reference for frequency, phase, and even amplitude of the incoming signal, which means basically this other laser has to be basically the same frequency as your incoming signal. So what does that mean? So when people built 100 gig transceivers, what they did was, instead of putting a second laser on them, which adds a lot of expense, that laser is the single most expensive thing on the device, they basically split the transmit laser, and they used it also as the local oscillator, which they combine with the receive signal that's coming in. And what that basically means is, since your transmit laser and your receive laser are the same, that means your transmit and receive frequencies have to be the same as well. So 100 gig doesn't lend itself well to single fiber. We recognize that as a real money-saving application for our customers and got a lot of requests. So what we did was we utilized our FPGA technology and our fabric. Remember this, our optical transport platform is also an OTN switching platform, so we can switch across the fabric. And basically what we did was we used the transmit on 100 gig CFP and the receive on the other. So now we have two different wavelengths that we can run over single fiber. And functionally what we can do is we can create 200 gig muxponders, 10 by 10 gig into 100 gig, with these two cards, using the transmit and receive of the individual CFPs. So if you look to the left, this kind of lays out how we do it. Card 1 is on the left. You see a bunch of 10 gigs, which are the SFP pluses that are muxing. And then you see a local CFP. Same thing for card 2 on the right, and its local CFP. And so what we're doing is, if you look at card 1, is we take its transmits and we transmit on the local CFP and we receive from the remote CFP. And we do that for the 10 gigs, do just the opposite for the 10 gigs on the other muxponder. So we receive from one CFP and we transmit on the other, which gives us two nice CFPs. So we can do single fiber transmission, and surprise, surprise, that same blade that I told you was a transponder, a muxponder, a switch blade, it's also a muxponder, single fiber muxponder as well. Saves our customers thousands of dollars per month because usually, especially if you're leasing a fiber, if you're going any significant distance, it's going to cost you a lot for each of those fibers. So you can eliminate one, you're generally saving on the order of $1,000 or more a month. So great return on investment. And by the way, this doesn't add any new cards or any new CFPs. So your sparing is with your same dual fiber muxponder and your same dual fiber CFP. It's the same hardware. All right. Use case 3, circuit emulation. That was the other one that I talked about a little earlier. So you're wondering, how in the world could I possibly do circuit emulation on an Ethernet switching device? Well, we had a customer that wanted to pick up legacy stuff, but he didn't want to do it over that Sonnet fabric that we provided him. So he wanted to do it over circuit emulation. So if you remember correctly, what I told you was on our switch fabric for our Ethernet, our ultra-converged broadband platform, which has Ethernet switching, we used an off-the-shelf switch ASIC, but we also laid down an FPGA to do other stuff. So we repurposed part of that FPGA basically to be a Sonnet aggregator. So then what we were able to do is just produce both low rate and high rate PDH and Sonnet cards for this chassis. And then if we wanted to aggregate DS1 traffic, for instance, into OC3 traffic, then we could do that on this FPGA and then wrap it in Ethernet and just hand it off to the ASIC. So very nice capability we were able to provide because that FPGA was there, didn't change the cost of the card, didn't have to respin hardware, could do it very quickly. All right? So with that, in summary, technology continues to provide the opportunity for more programmability in technology or telecommunications products. As you could see from the IEEE data that I showed you, FPGAs still continue to ramp down in price very quickly and ramp up in functionality and down in power. So very nice technology to be using. The use of software-defined hardware provides many advantages in both transport and switching equipment. Number one is the ability to add technology improvements to products that are already in the field without respinning the hardware, as I showed you in the many use cases. Number two is the ability to implement features ahead of the market, as I talked about before, also without respinning the hardware, so we can do it relatively quickly. And number three is cost reduction through feature optimization and integration. And the examples I gave you were optimizing around the size of fabric by building it ourselves, and integration of multiple devices that we would have bought off the shelf into a single FPGA to reduce cost. So if you saw anything that you think is interesting, feel free to contact me directly, or you just want more information on FPGA technology and how it's used in transport equipment, you can certainly contact me directly. Here's my phone number and my email address. And if I can't answer your questions, I'll certainly put you in touch with whoever can. And with that, I'm going to hand things back to Alan to take questions.